Okay, class, second attempt at 8A problems. I'm probably just going to blast through all of this since I already did this one time and it didn't obviously record the audio. So I hope it records it this time. So there we go. I'm looking for my fake marker for the smartboard. So what is the octet rule? Octet rule is when you get S2P6 configuration from adding or subtracting electrons. Okay, so that means that something like oxygen with a 2s2, 2p4 wants to have two more electrons to get a -2 charge, so that it ends up with a 2s2, 2p6 electron configuration when it has a negative charge. That's what the octet rule is. How many electrons must a sulfur atom gain to achieve? So sulfur is neon 3s2, 3p4, same thing as oxygen. 2 extra electrons gives sulfur a -2 charge, and it also gives it a 3s2, 3p6 electron configuration. So this would be where my octet rule is. The 2 and the 6 give us a total of 8 and a -2 charge for sulfur. So if an atom has the electron configuration of 1s2, 2s2, 2p3, how many electrons must it gain to achieve an octet? All I'm doing is knowing that p6 is what my target is. So if it's 2p3, that means I need 3 more electrons to give it, not a -6, to give it a p6, which means that well, first of all, I take a look at 2p3, and in the 2p, I have taken a look up. I have boron, carbon, and 2p3 is nitrogen, so I have nitrogen. And if I add 3 more electrons onto nitrogen, that gives nitrogen a -3 charge. So 3 more electrons, nitrogen with a -3. Use Lewis symbols to represent the reaction that occurs between magnesium and bromine. Notice the way I have my reaction written here. I have sodium giving 1 electron over to chlorine, and then on the other side we got the +1 and the -1. I'm going to do exactly the same thing here, except this time magnesium doesn't have 1 like sodium, but it has 2 because it's in the second group and it has 2 valence electrons. Notice for bromine, and I'm going to use a different color here just because I think it makes it a little bit easier to see. Bromine is in the 7th group right before the noble gases, which means that it has 7 valence electrons, and I have 1 spot here where an electron can go. Notice that over here magnesium has 1 that it can put 1 electron right in there and gets rid of that 1 electron. And then I have another bromine because I need more than 1 bromine because each bromine can only handle 1 extra electron. So I have now 2 bromines and 1 magnesium, and magnesium gives both of its electrons over to 1 bromine each like that. Which means that on the other side then I would get magnesium with a +2 here without any electrons, and then here I would have 2 bromines, but each one would have a -1 charge, and I can show you where that extra magnesium, I did that backwards, but you get the idea. 1 comes from magnesium, and the rest are from bromine, and then the -1, and then the 2 here means that we have 2 bromines for this. This is all exactly the same stuff that we've done before. You guys remember back in chapter 2 we talked about the +2. Bromine has a -1 because of where it is, and then we do our crisscross like this, and I get MgBr2. It all comes from the same place. So MgBr2 is exactly the reason why we have what we have with the valence electrons and how they move. Moving on, list the individual steps of constructing a Born-Haber cycle. If we're starting with the formation of CaBr, so if we're going to start from the beginning, I'm going to follow the same steps that we did for Na plus Cl. So I'm going to start off with calcium as a solid because Calcium is a solid at room temperature in its natural state, and bromine is Br2 like this, and it's a liquid in its natural state. So my first step is to change both that to a gas and this to a gas. So I do that like this. It's called delta H formation of vaporization, and I get calcium as a gas like that, plus bromine as a gas like that. And that's my step, changing from solid to gas and liquid to gas. And then I change again. My next step, this should be a Br2. I just forgot to put it in there. My next step, notice that this goes from a solid to a gas. This one's already a gas, but here they break up the bond between the Cl2 to just get one Cl. Well, we're going to break up the bond between the Br2 here, and that's going to look like this. I keep putting an S for this. It should be a gas like that. Plus, and then I get 2Br. This is how I show that I broke up my bond. My bond would be between Br and Br like this, and when I break that bond there, what I end up with then are two separate Br gas atoms. And then after that, I jump up here. I'm going to do my first. I know I'm going through this quickly. I apologize. There is an explanation in the book for this example I have on the right-hand side with sodium and chlorine. But I'm going to go through my first ionization energy and my second ionization energy here. And that's going to be for calcium. That's going to give me a +2, plus 2 electrons, just like that, plus then 2 bromines that are gases like that. So what I did was I ripped 2 electrons, these 2 electrons, off of this calcium to get a +2 for the calcium. Now, putting electrons onto an atom is called electron affinity, and it always gives off energy. So that means Ca with a +2 as gases here, plus, and now when I put the 2 electrons on here, I have 2 bromines, and each one is a -1, and they're still both gases. So when this happens, this is an exothermic reaction. It's not the biggest exothermic reaction that's coming up. So after I get the +2 for calcium and the 2 -1s for bromine, then my last step, this is the last step, I'm going through this pretty quickly, is when I hook them together, giving off lattice energy like this. And that means that I have Ca with Br2 like this, and it turns back into a solid. And this is the biggest exothermic part of my reaction. Okay, moving on. Which of these elements is unlikely to form a covalent bond? So, well, first of all, covalent bonds are between nonmetals and nonmetals. So we can get rid of that because potassium is a metal. So it would be very unlikely to form a covalent bond because it's already a metal, which means it's not covalent. The other one, of course, would be argon. Why argon? Well, argon is a noble gas, which means it doesn't want to actually bond with anything. So that one, for noble gases, it doesn't matter if you call it a covalent bond, it won't form any bond. So both potassium and argon would be unlikely to form covalent bonds. The last one here, you can do this 2 ways. You can, if you're a numbers person, you can take a look at the electronegativity, image on in the periodic. In the book. I forget what page this is. I'll take a look and write down the page number in a minute. But take a look at this image here. Here we have fluorine is up here in the upper corner. Another way you can do this is the closer to fluorine you are, the smaller the difference in electronegativity. So if you are talking about oxygen right next to each other, then these two would have the least least difference between the two electronegativities. In actuality, it's 4.0 and 3.5, which is a difference of 0.5. Okay? So if you take a look at carbon and fluorine, so here you have carbon and fluorine like that. I put a circle around both of them. Carbon is 2.5 and fluorine is 4.0, so that's a 1.5 difference. So this would be the closest or the smallest in electronegativity. This would be the next. And then, of course, beryllium like that would be the furthest away from each other. So that would be the highest difference in electronegativity, when in actuality it's 1.5 and 4.0, which gives us a 2.5 difference. You can do the same thing with all of these. The ones that are further away would be more of a difference in electronegativity in general, or you can actually use the numbers that are on this chart here. Okay, you could do it either way. I'm expecting you guys to fill in B and C and put them in order of increasing from lowest to highest, which is increasing electronegativity. All right, nice work.